Good morning, everyone. This is Carl Griffith from Graybar, and I want to welcome you all to our G2 Talk webinar series, where today we're going to talk about power over Ethernet. Before we get started, I'd like to bring a few things to your attention as we go through the webinar. First of all, thanks for your attendance. There is an opportunity for questions and answers in the presentation. So at the bottom of your screen, you see a little tab, a little button marked Q&A. If you'll press that, a dialog box will open up, and you can type your question in there. At the end of the presentation today, there will be time when we'll go through those questions, and we'll respond to as many of them as we can online, so everybody can participate in that. So type your questions in that Q&A, in that little dialog box as we go through. We'll pick those up, and at the end of the presentation, we'll go over them. If you're one of the first 50 people to register and to log on to the webinar and stay with us, we're going to provide you with a special gift. Watch your email in basket today, and you'll receive a certificate for a cup of coffee for a major coffee chain in North America, so I guess worldwide. But that cup of coffee is on us, and we're just so honored to have you with us. We're happy to reward you with a cup of coffee. As we continue down this path, one of the things that we're working on here at Graybar is the existing building inventory that exists in the United States. There's billions of square feet of existing buildings that are in the United States that haven't been upgraded in 20 or 30 years, and we're looking at upgrade opportunities inside those buildings. And we identify that program for the retrofit and renovation of commercial buildings as Power Smart. So our themes within the G2 Talk webinar, they respond around Power Smart. And Power Smart kind of can be something like this. We power and we illuminate and we network and we secure buildings with speed, intelligence, and efficiency. And that's what Power Smart's all about. This whole theme today about power over Ethernet hits that mark very well about what we can do in the renovation and retrofit of existing buildings. So without, one more thing. We archive everything. So if you have to leave this presentation early, you can always come back and get it. If you would like to share this presentation with somebody, if you go up to graybar.com, click on the G2 Talk logo, you can get to the archive. And you can see this presentation, which will be archived, or any of the other G2 Talk webinar series that we've had. You can get that complete archive. So I don't want to hold up any more time from our speaker today, and I'm just so excited to have Valerie McGuire with us from the Siemon Company. I've known Valerie for quite some time. Way back in the day, I would sit on TIA committees, and Valerie would be there, and I've always been I admired her for how much she knows about this whole industry that we have on balanced twisted pair and optical fiber and telecommunications, cabling and transmission theory. She's absolutely a subject matter expert on the entire subject of structured cabling. I just found out today that she's a UConn grad, so she's a Husky, and I'll congratulate her on her big win this year for that. Valerie has served in leadership positions and served on committee work at TIA for, I guess, accumulated as many as 16 years she's been doing that, which is just absolutely amazing. She's also participates as on IEEE 802.3 work. She does that and sits as chairpersons in different leadership positions there as an officer on IEEE. One of the biggest titles that I think that we can put on Valerie, not to say we want to put it on her, but Cabling Installation and Maintenance Magazine recently had a list of the top 20 positive contributors to the cabling and network industry, and I'm just very happy to let you all know that Valerie is on that list. And just a side note, she's the only woman on that list. So without any further holdups in Valerie's presentation, I'd like to pass the baton over to Valerie and ask her to provide us with as much input as she can today about this exciting subject of power over Ethernet. Thank you, Valerie, for joining us today.
My pleasure, Carl. Thank you so much for having me, and thanks to the audience in attendance. Today's presentation will be focused on the subject of remote powering. And this is a very critical technology for supporting not only the Gray Bar PowerSmart program, but all voice, data, and technology applications, including building system applications, over the familiar structured cabling infrastructure. Now, you might have thought that you've heard it all about remote powering, and when you think of remote powering, you probably are considering applications like voice over IP and IP cameras. But remote powering really goes well beyond that. And in fact, what 10 years ago we would have considered rocket science is actually available today over structured cabling using remote powering technology. What is this rocket science? Television. I don't think that there's anyone on this call today that 5 years ago would have predicted that there is a company called Aquavision based out of the United Kingdom that can not only provide data, but power 22 and 27-inch televisions with Category 5E cabling. This technology is absolutely amazing. It relies on HDBaseT signal transmission and power over HDBaseT technology to deliver video and power over one Category 5E cable. I love the slogan for this company, Aquavision. They say they're often copied but never equaled. Aquavision is the ultimate in luxury, the leading manufacturer of waterproof, flush, and in-wall televisions. It's the first choice for the discerning individual. So as you can see, I hope you're getting excited about the capabilities of structured cabling, what we can do with it beyond simply supporting voice and data. So there might be some new folks on the call, and just to make sure that we're all using the same language, I'd like to go over some fundamentals. First of all, what is remote powering? It's simply running power at the same time as you're running data over a structured telecommunications cable. The DC power can be injected over a pair that's carrying data or a non-data carrying pair. Power can be injected in one of two ways. It can be injected by the switch. This is called end-span power insertion. Or it can be injected by a device that's inserted into the telecommunications channel, like a power patch panel. This would be called mid-span powering. Now, you've heard me say several times remote powering, and most people think remote powering is the same as power over Ethernet. And yes, while power over Ethernet, or PoE, is probably the most commonly recognized remote powering application, it's not the only one. For example, POH, as we discussed, supporting the Aquavision television, is an example of a non-PoE remote powering application. So in a nutshell, there's a lot of advantages to supplying DC power over your structured cabling plant. Ease of installation is certainly one that comes to mind. The safety of supporting DC power delivery using safety extra low voltage applications, the improved safety due to separating the power to these devices from the building's main AC power ring. We also can experience significantly lower power consumption, as well as reduced operational costs for applications such as voice over IP, which replace the traditional analog telecommunications billing infrastructure with a networking billing infrastructure. Where is the device technology today? Well, power over Ethernet is broadly available. In fact, there are over 100 million PoE-enabled ports that are shipping annually. PoE is available in several flavors. The first PoE technology is called Type 1 and delivers 15 watts of power. Up until the last year or so, Type 1 PoE was really sufficient to support all of the applications. Now we have 802.11ac wireless access points that require more than 15 watts and in fact require the 30-watt Type 2 PoE application. We talked about the powering of televisions, and there's new technology that's emerging, such as Cisco's 60-watt universal PoE technology, and technology that's under development by the 802.3 BT 4-pair power over Ethernet task force. When we talk about specifications for power over Ethernet, there's a couple capabilities that we need to understand. and acronyms. The most common acronyms are PSE and PD, and these are used in the specification of the remote powering standard. PSE stands for Power Sourcing Equipment, and that's the device that injects the power into the channel. And the standards specify the maximum continuous output power that's delivered by the PSE. The standards also specify the maximum power that's received by the powered device. As you can imagine, there are some losses across the structured cabling channel. So the performance parameter for output power at the PSE will be slightly different than the power that's available to the PD. And these parameters are important for the specification of remote powering devices. This chart shows an example of 3 common devices and technologies that are available today in gray, as well as the new technologies that are under development by the 802.3b task force in red. So here you see again the Type 1 and Type 2 Ethernet applications. Type 2 Power over Ethernet is often called Power over Ethernet Plus. Interestingly, if you were to go into the standard, that terminology actually isn't recognized in the standard. It's kind of a term that the industry has adopted. And you can see that Type 1 and Type 2 PoE apply 15.4 or 30 watts of power from the power sourcing equipment. And this is done over 2 pairs. Well, to get the power levels that we're looking at for beyond simply powering wireless access points and cameras, the types of power levels we need for supporting televisions and perhaps tablets and cloud-based devices, we need greater levels of power to be able to transmit over the structured cabling. So this means that instead of just powering 2 pairs, the latest technology is going to be powering 4 pairs. The Power over HDBaseT technology that we discussed for televisions, in fact, delivers the maximum allowable 100 watts of power over structured cabling. The 4-pair PoE Type 1 application is currently targeted to provide 60 watts of power over 4 pair. There is a proposal as part of this project to also specify a Type 4 application with perhaps also 100 watts of power provided over each pair. So if we start back at the very beginning, when Power over Ethernet was initially thought of, our idea was to support network cameras, wireless access points, radio frequency ID tags, and Type 1 PoE is perfect for building automation systems, thermostats, smoke detectors, alarm systems, so forth. All the devices that are in the sweet spot of the gray bar power smart technology grouping. But the power levels to support these devices, only 15 watts, is not sufficient to support next generation devices. We were very successful with Type 1 PoE. The reliability, the cost break makes this something that people are rapidly adopting. So in the standards organizations, we're always looking to the future. Where can we apply greater levels of power? One of them we already talked about was the 802.11ac wireless access points. This new 5 gigahertz technology simply needs more than 15 watts of power to be able to transmit and support wireless devices. There's also, as I mentioned, the potential for thin clients, laptop computers, as well as even long-distance wireless devices. So lots of opportunities here if we can get those power levels up. Probably the most compelling application is Power over HDBaseT. And this is a 100-watt application that's delivering 100 or supporting 100 watts over 100 meters of Category 5E or higher cabling. So in a typical POH implementation, the power sourcing equipment is installed and powered by a 50 to 57 volt DC power supply, kind of like a set-top box. And all the devices that are connected to that power supply receive the power directly over the HDBaseT link across all 4 pairs of the Category 5E or better cable. The HDBaseT Alliance said that the Power HDBaseT specification is trademarked for under the terminology 5-play. And the idea here is support of 5 technologies: video, audio, Ethernet, and control via standard LAN cabling. The beauty of these types of systems is that they reduce overall network power consumption, and they enable flatter, thinner, lighter, and more cost-effective television solutions to be implemented. Now, there are ramifications and implications, both electrical and mechanical, for applying these types of power levels over structured cabling. Now, the first is what happens when I break connections when DC power is appearing across the conductors in a twisted pair circuit. Telecommunications modular plug-and-jack contacts are very carefully engineered, and they're plated typically with gold or palladium to ensure a reliable, low-resistance mating surface. Today's remote powering applications, specifically Power Ethernet applications, offer some protection to these connection points by ensuring that DC power is not applied over the structured cabling plant until a powered device is sensed by the power sourcing equipment. Unfortunately, unless the power device is shut off beforehand, the power sourcing equipment doesn't know to discontinue power delivery if the modular plug-jack connection is disengaged. So this condition is commonly referred to as unmating under load, and it does produce an arc as the applied current transitions from flowing through conductive metal to flowing through air before becoming an open circuit. Now, I want to emphasize that the current level that's associated with this arc poses absolutely no risk to humans. However, this arc does create an electrical breakdown of gases in the environment surrounding the contacts that potentially results in corrosion and pitting damage on the plated contact surface at that arcing location. So this is something that we need to consider when specifying products to support high DC power currents of 30 watts and higher. So there are designs of connectors that can help us to overcome this arcing situation. Now, it's important to remember that the arcing is unavoidable. It's always going to occur when I break an electrical contact. But I can design the contacts in such a way as to ensure that the arcing occurs in the initial contact or wipe area and doesn't affect mated integrity in the final seated contact area, which is actually shown in this picture here. Now, the good news is that we do have a standard. It's IEC 60512-99-001 that was specifically developed to ensure reliable connections for remote powering applications deployed over balanced twisted pair cabling. So the first thing we've learned here today is when specifying cabling systems supporting high current remote powering applications, ensure that you're selecting and specifying connecting hardware whose contacts have been designed in such a way that this arcing occurs in a different position from the final seated contact position. Specify components that are compliant to IEC 60512-99-01. Now, I do want to take a minute to tell you I do work for the Siemon Company, so obviously all of our DMAX and Terra products do comply with this specification. You don't need to ask that question. All right, so moving right along. We talked about arcing conditions. When I specify the requirements for the PSE output power and the power received by the power device, as I mentioned, there's a difference. There's some losses in there. Those losses occur as a result of impedance within the cable, and those losses create an artifact, which is increased temperature rise within the cable bundle. So this has implications for the operating range of structured cabling, which is specified to operate up to 60 degrees C. We don't want to have excessive temperature rise in the bundle that exceeds that 60 degree C operating environment, so that's something we need to talk about. And we also need to take into consideration the mechanical performance of the cabling. What operating temperature are the cables specified for? If we exceed the operating temperature, we do risk the potential that the jacket materials will age prematurely. That means they may become harder or brittle sooner than they were designed to. Now, I want to emphasize that the types of temperatures we're talking about are about 120 to 140 degrees Fahrenheit in the worst case environment. So you're at the top of the operating range and you have a little additional heat that's caused by the remote powering application. These elevated temperatures do not result in cables melting. They do not create safety risks. They result in increased insertion loss and potential for mechanical degradation of the cable. So what type of elevated temperatures are we talking about? Well, this is a chart here that was developed to demonstrate what happens when the current, the 600 milliamp current associated with the PoE type 2 application or the PoE Plus application is applied to 100 cable bundles of different grades of cabling. What we see here at the arrow is that current associated with type 2 PoE, and I'll share some numbers with you. The temperature rise within a category 5E bundle is 7.2 degrees Celsius. And category 5E is the minimum grade of cabling recognized for support of the PoE type 2 application. As the category or performance rating of the cable increases, a couple things happen. The conductor size gets larger, there may be the presence of an overall foil, and there may be the presence of an overall foil or screen. Now this chart clearly shows that the more metal, larger conductors, more foils or braids that are part of the cable design, the better the heat dissipation. In fact, the heat dissipation for a category 6A FUTP cable, the temperature rise that's associated with deploying a PoE type 2 application, is only 3.8 degrees C. The temperature rise within a category 7A bundle associated with the PoE Plus application is 2.8 degrees C. So let's talk a little bit about what we've learned here. We know that remote powering applications cause some heat to build up in the cable. We also know that there's no method to cool down hot pathways, and there's no way to monitor temperature rise. So the industry rule of thumb to deal with the worst case expected temperature rise is to reduce the maximum operating temperature specified by the standards from 60 degrees C to 50 degrees C. Now, 50 degrees C is about 122 degrees Fahrenheit. For the Northeast, that's not a problem. I'm based here out of Phoenix, Arizona. This is a problem. We can easily experience these types of temperatures in enclosed ceilings, plenums, and riser spaces. These are also concerns other areas of the American Southwest, Texas, the Middle East, Australia's Northern Territory, and other places throughout the world where we can achieve an elevated temperature. So simply saying I'm not going to install structured cabling in an environment that exceeds 50 degrees C can be problematic for some installations. Now, fortunately, there's a solution. There are cables, such as the Siemon shielded Category 6A and 7A product line, that are qualified for mechanical reliability to higher temperatures. Our systems are qualified for mechanical reliability up to 75 degrees C, which is 167 degrees Fahrenheit. And these cables are going to exhibit superior heat dissipation, and as a result can be installed in environments up to the maximum TI operating range of 60 degrees C. And they won't experience mechanical degradation caused by the combined effects of high temperature environments and heat buildup within the cables. Now, many folks are not aware that insertion loss increases as cabling temperature increases, and both TI and ISO specify temperature derating factor that reduces the overall horizontal cable length at temperatures just above 20 degrees C. And here in this figure, you can see in red the derating profile for Category 6A unshielded cables. This is length derating, how much I reduce the overall cable length depending on the temperature above 20 degrees C. Now this red curve has a profile that is 0.4% increase in insertion loss per degree C from 20 degrees C to 40. And then at 40 degrees C, you can see there's a bend. The slope increases to 0.6 degrees from 40 to 60 degrees C. This is a much more serious or much more stringent derating adjustment than specified for shielded systems, which are just 0.2% increase in insertion loss per degree C over the entire range of 20 to 60 degrees C. Now, this is complicated. What's the takeaway? The takeaway is pretty simple. It's telling us that shielded systems have more stable transmission performance at elevated temperatures and therefore are more suited to support applications such as PoE Type 2, such as POH, and the emerging Type 3 and Type 4 technology. One thing I do want to mention is what is the implication of this chart. The implication is for a 100-meter structured cabling length with a 6A UTP channel, that length of the overall channel has to be reduced to 82 meters to still meet the TI insertion loss requirements at 60 degrees C. The overall length of a shielded 6A system only needs to be reduced to 93 meters to meet those requirements. So this does have implications for structured cabling deployment supporting remote powering applications over long lengths. I'd like to chat just a minute about deployment of BAS applications. According to TIA 862A, there's a couple different ways we can support device connections. We can support connections to telecommunications outlets directly from distributor A or the interconnector patch panel in the closet. There are also provisions for using a horizontal connection point that's enclosed within a zone box that can facilitate direct connections to the BAS device or connections to an equipment outlet that support the BAS device. So there's lots of flexibility. But along with this flexibility, there's implications for cable selection. The Siemon Company recommends for ease of deployment, ease of administration, supporting moves, adds, and changes in labeling, that BAS systems be supported using a topology similar to what's shown in this screen. So we have a horizontal connection point that's located in the zone box, and we always have the optional equipment outlet in place, and that facilitates device connection. So here you see a zone-style star topology IP-based surveillance system. But there are implications that are associated with the cable selection here. Obviously, in a type of topology like this, the horizontal cable segment would be solid, and naturally, a stranded cord would be used from the optional equipment outlet to the camera. But the BAS standard does allow a provision for the optional equipment outlet to be removed from the system. And in that case, we have a direct connection from the HCP in the zone box to the camera. And I do want to emphasize that that connection should not be made with stranded cable. It should be made with solid cable. So this means I need a solid interconnect cord from my HCP to my camera if I choose not to employ an equipment outlet. Now, why am I recommending solid? Well, there's a couple reasons for that. The first reason is typically these connections would be longer than 10 meters. So by using solid cable, I eliminate the necessity to length derate the channel to accommodate excessive stranded cordage lengths. But the other reason is that it's a known fact that stranded conductor cables that are used to construct patch cords have much greater insertion loss due to elevated temperatures. And where are these devices located most commonly? Most commonly, they're located in the ceiling space that's not an environmentally controlled position. So fortunately, the risk of performance degradation due to elevated temperatures in a zone cabling environment can be very well mitigated by using solid conductor cords for all of the equipment connections in the ceiling. And again, based on what we saw on the characteristics of heat dissipation for shielded versus unshielded systems, the recommendation would be not only to use a solid conductor cord, but also to use a shielded conductor cord. So this will give us better heat dissipation and products that, and an opportunity to have access to products that are characterized up to above 60 degrees C. I want to talk a little bit about products that are designed beyond the standard 60 degrees C operating range. I'm going to be looking at the Siemon Category 6A and 7 product line, but this type of analysis can be applied to any other vendor that has cables that are characterized for greater than 60 degrees C. The takeaway here is, the shielded cables exhibit extremely stable transmission performance at elevated temperatures, and they require less length reduction than specified by TI and ISO to satisfy insertion loss requirements. This is important because it provides the cabling designer with significantly more flexibility to reach the largest number of work areas and devices in a converged cabling environment. So as shown here, you see in red and blue the derating distances that we discussed, excerpted from the TI and ISO standards, but you see in cyan, a Siemon Category 6A FUTP cable, you can see even better length derating. In fact, the derating for our products at 60 degrees C is 3 meters, which means the maximum link length is reduced from 100 meters to 97 meters. So lots and lots of flexibility there. If you have a PoE application in a hot environment, you need to support a full 100 meters, well, Category 7A is a great choice because Category 7A solutions require no length derating all the way up to 70 degrees C. And in fact, these solutions can fully support remote powering currents up to 600 milliamps over all 4 pairs and all networking applications up to and including HDBaseT over that 4-connector 100-meter channel model. So lots of interesting things here. We've talked about mechanical and electrical implications of remote powering. So again, I want to emphasize the types of current levels associated with remote powering are very safe. They're not going to damage humans. They fall under the safety extra low voltage category, but they do have implications, and those implications affect cabling selection. The implications are temperature rise in bundles and potential for arcing when unmating under load. All trends indicate that we're migrating from 2-pair to 4-pair power delivery, and clearly greater than 30-watt capability is the future of remote powering technology. So my wish for you today was to take away a couple points. The first is, as the market for remotely powered IP devices grows and more advanced powering technology is developed, you need to be aware that the ability of cables and connectors to operate in higher temperature environments and perform under DC load conditions are critical factors in the long-term reliability of the cabling infrastructure used to support remote powering applications. The second takeaway is to understand that there are cabling products that are designed to operate under the demanding remote powering conditions, and these products are available today. And these include choosing cables that have improved heat dissipation properties, and finally, point 3, choosing connectors that are designed to handle the contact arcing potential during a mating under load condition. So I really hope that you found this information useful and helpful. I hope that you're as excited as I am about the future of remote powering technology. And I hope that at this point we've got enough time for Carl to field some questions my way. If I've overlooked anything, I'll be happy to share what I can and try to answer your questions. Thank you very much, Carl. I'll hand it over to you.
Thank you, Val. I have a couple of questions of my own that came to me as we went through the presentation, just to add a little clarity, if you don't mind. As the global SC for the Siemon Company, you meet with a lot of customers, both integrators, communications contractors, and end users. Can you give me a feel for what percentage of the people you talk to have a conversation, or you have conversations about PoE? I mean, how much is it in terms of on the mind of the people in the industry?
That's a great question, Carl. I think, with Graybar's Power Smart initiative, you know the answer, and that is every customer that I talk to is dealing with applications that they may not be thinking remote powering, but have implications for remote powering. And let me give you an example. Basically, every customer wants to know about 802.11 AC. That is a Type 2 powering application. It has implications. So I would say essentially every opportunity I have to talk cabling with customers brings up the topic of remote powering.
So switch manufacturers have been providing PoE ports on their switches. Do we know anything about the percentage of switch shipments and what the ratio of PoE-enabled ports is to non-PoE-enabled ports in terms of new purchases?
That is a great question. The industry, I don't have a direct answer, but I could tell you how I would calculate it. If I knew how many switches were shipping annually, I do know a total market. I do know that 100 million ports are shipping each year now that are PoE-enabled. I don't have an exact figure, but 100 million ports per year is outstanding. I do know that the prediction is that in 2 years, 40% of all wireless devices will support 802.11 AC technology. So I definitely see a significant uptick in the ability of these devices to support 30-watt capability.
My last question, and then we'll go to the questions that have come in from our attendees today, is early on in your presentation when we were talking about video, you mentioned 5-play. Is 5-play shipping in the U.S.?
That's a great question. The HDBaseT technology is primarily at this point dominated by audio-video products. And at the last this is not a setup question, Carl, because the name of the show eludes me, but one of the last major electronics show, there were 8 products that were available in the U.S. supporting 5-play technology. But again, they're primarily audio-type devices, so HDMI extenders and so forth. You can get a POH television here. That's the beauty of it. It's the same power system, but it's not commonly available, obviously.
All right. Okay, that's great. I think that show was probably the Consumer Electronics Show, CES.
Yes, thank you very much.
Yeah. So we have a couple questions here, and I'm going to go through these, and we'll get as many as we can. Tim asked this question: will the high power limit seen with the 60-watt, 100-watt levels in PoE be able to be classified as Class 2 or Class 3 circuits with the NEC 725? What kind of coordination is going on here between TIA and the National Electric Code?
Well, these products and these solutions fall under the SELV class, and Class 2 is typically reserved as a terminology for the injector. So that would be something that would be associated with a switch or a DC power injection device. These systems are allowed to support up to 1 amp and remain designated as a communications cable, which is a much lower classification than Class 2 or Class 3. I think one of the interesting things to keep in mind is, in fact, the type of power that we're putting has less energy than ringer voltage. So we're still very, very low levels.
All right. Thank you. And then, Michael, this is kind of follows the same vein here. What's the voltage here on PoE? We talk about the wattage, and we all know
That's a great question. It's 50 to 57 volts, and we need to remember that the current is applied over multiple pairs. So it's typically 50 to 57. Believe it or not, there is a new IEEE project that's looking at DC voltage in automotive applications, and that would be a 12-volt DC application when that is published.
Okay. John asked a question, and I'll read it to you because I don't quite understand what he's getting at here. But it says, also I would expect that PoE would be harder to implement in an area that requires Class 1 Division 2 compliance for intrinsically safe devices. Do you know what John might be talking about there?
I'm not exactly sure. We'll have to ask for a clarification, but sometimes questions like this refer to environments that maybe have oxygen in them or something that might be susceptible to a spark condition. Spark might cause a problem. I think we need to keep in mind that ringer voltage, again, as I said, will also create a spark. A funny story here, John Siemon relayed this to me. About 15 years ago, one of our engineers was doing some work at his house, and he was replacing the work area outlet and put the RJ11 cord in his mouth to just kind of hold it, maybe some screws and that. And the phone rang, and he actually got it on the tongue. So again, we need to keep in mind that the PoE voltage levels are extraordinarily low. And this is no different than ringer voltage type applications. We have been putting DC power over structured cabling now for years. If you think about the old phones you used to have before we went wireless, you could lose power to your house, but the telephone still worked because DC power was applied on those lines.
A good point. Just for those on the line with us, if we don't get to our question or we don't answer that question exactly as we wanted to, we'll respond to you via email when the presentation's over and respond to those questions that we weren't able to get. Chuck asked a question that I think is appropriate. When we talk about PLCs on the factory floor, we talk about utility subcontrol units and their power requirements. Has there been some work done in the industrial environment when it comes to PoE? Do you have any comments about that?
Let me think about this for a second. I think that I'm not a true expert on these type applications, but I don't believe that these are primarily, I think 50 volts is actually too high. I think these types of applications are typically lower levels, maybe 12 volts. I think this new automotive application that's under development has implications for industrial environments and probably would be what Chuck is thinking about. I'll make a plug here. The Siemon Company has a site that's called the Standards Informant, and it's really generic. It's not product-based, but if you click on the IEEE tab, you can learn more information about these under development IEEE technologies, such as 12-volt DC over 1 pair for industrial applications.
Right. Tim asked a question about, and he kind of asks it in a little different way, and I'm going to add a little comment to this too at the same time. Does not providing an outlet in the horizontal link meet the standard requirements for structured cabling TIA 568C? And I think we might be referring to the drawings that you showed up there where the work area outlet in this type of environment in building automation systems is optional. And just for the edification of those on the call, Graybar's been promoting this for quite some time with our Enable to Cable program when we talk about direct attach, where we put the modular plug directly on the horizontal cable in the environment where it's non-user administrated. And many times in a commercial building when you're with cameras or access points or other building devices, those are non-user administered. And that's a good opportunity then to put the plug directly on the end of the horizontal cable, which is a solid cable. And as you indicated in the presentation today, the insertion or the addition of a stranded cable may not be the right choice anyway. So any comment about the standards part of eliminating that work area outlet?
Absolutely, Tim. That is a very observant question, and there's a subtlety here. Within the 568C standards, we have a terminology called a telecommunications outlet, and within the BAS standard, we use a different terminology, equipment outlet. So if you were to do a search in 568C, you would never see equipment outlet used. It's always a telecommunications outlet that telecommunications outlet is mandatory. 2 ports serving that telecommunications outlet in the work area. With the equipment outlet, however, it is a different setup. And as Carl mentioned, if you have a horizontal connection point in place, that equipment outlet is optional. The Siemon Company recommends the use of the equipment outlet because, again, it facilitates labeling, it facilitates administration. But as Carl mentioned, it is very common practice to provide an interconnect cord that's solid to the device, back to the interconnect panel, and that is allowed by the standards. I guess, Carl, the analogy that I would use is it's kind of akin to the decision, do I use a patch panel or do I use an interconnect in the closet? There's sort of 2 patch panels to facilitate a cross-connect, or do I use an interconnect? It's really by providing the equipment outlet, you have some additional flexibility for administration, but it's not required. Does that help answer that, Carl?
It did for me, but we can add more clarity when we share these questions with each other on a spreadsheet, and then we can maybe reply with a little bit more detail. Jacob asked a question about the effect of heat on jackets in this PoE environment. Is there a difference between a plenum-rated jacket and a non-plenum-rated jacket in terms of how the heat affects the jacket?
Yes, there is. It's statistically very small, but plenum and riser cables, depending upon their design, do perform differently. But again, it's not significant. The temperature rise between a 5E riser and a 5E plenum is within 1 degree Celsius. If you remember from my chart, I showed the maximum temperature rise in the TIA experiments for category 5E was 7.2 degrees. This included both riser and plenum, and that 7.2 degrees was rounded up to 10 degrees C to come up with the worst case rule of thumb, don't install above 50 degrees C, to accommodate all the different variations in the cable jacket construction and the conductor constructions as well.
Right. There's just 2 more questions, and we need to go because we're running out of time here. We'll respond to every question via email. Is the 50 to 57 volts AC or DC?
Always DC.
All right. And then the last comment was Lou indicates to us that his understanding that telephone ring voltage was 130 volts DC and the voice level was 51 volts. Did we miss something here?
Well, the currents are different.
Right.
Is the difference between the application, and in fact, some ringer voltage can exceed 300 volts.
Right.
That's something that we can look into more and give a reference to a table. But there's a lot of variance in ringer voltage. If you think of devices, the old days where we'd have those flash current devices that would fit on top of a 110 block, and Carl, I know what you're talking about, sort of 66 block, like these Pico protectors. Those devices could be rated to break down all the way up to 350 volts. So there are applications for the appearances up to 350 volts on a 66 block that have been around for decades.
Well, Valerie, I really want to thank you for being with us today. Just for everybody online, I wanted to remind you about the archive. This presentation will be archived. You just go to graybar.com and click on the G2 Talk logo, and you can get to the archive. The first 50 people that are on here today, they're going to get that email for a cup of coffee. We're glad to do that. All the questions that we didn't get to, we will respond to you via email. Those will be shared with Valerie and myself, and we'll make sure that we respond to you correctly with that. We want to thank everybody for joining us today. We look forward to seeing you next month. Thank you very much again, Valerie, for the time that you spent with us today. Everybody have a great day. Thank you.
Bye-bye now.
Bye.